Hi everyone, welcome to my presentation today. So today I would like to discuss about the air toxicants, styrene and SBTEX, their emission estimate and the concentration estimate for the US Gulf region. So this is my today's outline. First I will introduce the research background, and then I will introduce my research scheme, and then I will talk about the method and the result part. So this is the background part. So styrene, benzene, toluene, ethyl benzene, and xylene are hazardous air pollutants, or we call it HAPs. And they are come from combustion, vehicle emission, and solvent usage, and the petrochemical industry. So the middle part, it shows the chemical structure of SBTEX. And the right hand side figure, it shows different source contribution from different type of emissions. So why the SBTEX are so important? Because they have half effect. The SBTEX can affect the kidney, liver, and blood system. Some species, they also have the long-term effect and lead to cancer. Because the largest US SBTEX production facilities are in the Gulf region states. Therefore, the latest study also indicates that the SBTEX can cause the neurologic symptoms based on the blood sample study. And in the right hand side, it's a figure shows that the SBTEX and other HAPs can affect the human organs and cause some different symptoms. So can we estimate the SBTEX concentration in Gulf region? So to do the human exposure study, so we think the chemical transport model CTM can be used to simulate the concentration of SBTEX. But how? Because the CTM model usually used to simulate the ozone and PM, but not for all HAP species concentration. For example, the STEX species are not considered as the explicit species in current reduced chemical mechanism in CTM. So the STEX species are surrogate to tau and xyl. Therefore, we apply the US EPA NEI with smoke model to calculate the individual SBTEX emission data, and we introduce the reactive tracer method to simulate the individual SBTEX. So this is about my research method scheme. So in this part, we have three different parts. The emission part. First, we apply the NEI and smoke model to estimate the HAPs emission. And we also make up the missing HAPs emission. Then we generate the full emission for the CTM model usage and the SBTEX emission only for the reactive tracer method usage. So in the full emission part is applied into a CTM model. We call it base model. And in this CTM model, it's with the reduced chemical mechanism CV6R4. And we process the CTM model and get the model output for different species and radicals. So we also compare this base model result with the TCEQ SIP model data and the AQS observational ozone data to verify our base model works. And in this base model, it calculates the hourly OH radical, nitrate radical, and ozone concentration. So in the reactive tracer part is a post-process of CTM model. It's apply the hourly radical concentration with the SBTEX emission to estimate the chemical decay. And the other decay parameters are considered the NIST database parameters. After the RT-RSC process, then we can calculate the SBTEX concentration. And we also apply the MTEC observational data to analyze the result. So let's take a look for the emission part 1. So this table shows the total SBTEX emission data in 2011 NEI by different emission sector in column and the different species in row. So in the species part, there are I and M in the end. It means that the inventory species and the model species. And following this table, we figure out that the largest contribution of SBTEX emissions are happened in on-road sector. And the second largest one is the PT Fire 3D. And when we compare the benzene inventory species and the Benz model species, we figure out that some sector they are the same, which means there is no problem, but for some sector, they may have the missing data for the HAPs. Okay, so this part is about how we do the gap field process for the missing HAPs emissions. So first, we have the county level and the SCC level inventory report from the smoke output. And in this report, there are annual emissions by county and the SCC. So in this data set, we separate the data into two groups. The data with HAPs emission and the data without HAPs emissions. And we compare these two groups and find the same SCC happened in these two groups and only happened in Gulf region. And then we apply the HAPs and the VOC ratio in the with HAPs group and use this ratio to estimate the missing HAPs based on the VOC total times this HAPs and VOC ratio. So following this method, then we can get the emission for individual HAPs. And for the benzene, we just adjust the benzene emission to the same with the Benz directly. So this is about the emission part 3, the missing SBTEX emission data. So in this table, the column indicate different states and the row indicate different species happen in different sectors. So following this table, we figure out that the Texas have the largest missings, and this happened in the non-point oil and gas sectors. And the second largest sector is happening in the PT non-IPM. And the second largest state is for the Louisiana. We make an additional NEI emission data for the smoke input, and we reprocess the smoke model again to do a gap fill for these missing emissions. After that, we apply the emission data into the CTM model. So the CTM model, the version is CAMX 7.0 and the simulation period is from 2012 May to September, and the meteorological data are from US EPA and the post-process are made by the WOLF CAMX and the MCIP. And the model domain is from 12 km times 12 km, and we did the flexing nesting to 4 km. So the blue rectangle indicates the 12 domain and the red rectangle is the 4 km domain. And the chemical mechanism we apply is CB6R4. So what is the reactive tracer? So it's a tracer species but simulate the process consider chemical decay. So as everyone knows, this is the chemical reactions. A plus B as a reactant, and it's become X plus Y is the product. And the reaction rate constant is K. And so the real reaction rate is concentration A times concentration B times K. So in this study, we get the reactants from the smoke emission model. So these are 5 HAP species SBTEX. And then we have the oxidant agent from the base model is OH radical, ozone, and nitrate radical. And then we find the rate constant from the MCM mechanism. And those are the rate constants for each species and their reactions. So this is the reactive tracer model result looks like. So it's an hourly concentration data, and we can see their pattern are followed by the diurnal pattern and have the wind direction and wind speed effect and PVL effect. And we can also do the grid cell average by different month. So this is the toluene concentration monthly average. To verify those reactive tracer data are reliable, then we also compare with the MTEC observational data. So the MTEC is made by US EPA, and the sample duration have 1 hour in Texas, 3 hours in Louisiana, and 24 hours for both Texas and Louisiana. And those are the species that the MTEC data provide can compare with our model. Okay, so let's take a look for the result 2, the reactive tracer model result compared with MTEC measurement data. So this comparison is based on the daily average for each different part. So the data is based on May 1st to September 30, and we have total 151 days data. And in the figure, the R is the correlation coefficient. So in this figure, the upper panel shows the Louisiana's comparison, and the bottom panel shows the Texas comparison. So each different column shows different species. The first column is xylene, and the second column is toluene, and then styrene, ethylbenzene, and benzene. So for each individual figures, the x-axis is the observational data, and the y is the model estimate. For the each single point, the blue point is the emission without do the gap filling, so it's the original inventory data. And the right triangle is the adjustment data after we do the gap fill for the missing emission in the SEC and county level. So following this figure, we conclude that the xylene, toluene, and the ethylbenzene, they have better results. But for styrene, especially in Texas, it looks like it have overestimate in the low concentration, but underestimate in the high concentration. And for the benzene, it shows like the benzene inventory is underestimate, and the benz as the model species is overestimate. Okay, let's take a look for the result 3, the reactive tracer model result diurnal pattern compared with the measurement data. So these data are based on the hourly data over May to September, and all data are considered in 6 sites in Texas only, because those are the hourly data available. And there are 5 figures here, and each figure indicates different species. So in this figure, the x-axis shows the hour of the day, and the y-axis shows the concentration, ppb. So in this box, the gray box shows the observational data, and the blue box shows the original inventory data without adjustment, and the red box shows that we did after we did the gap fill for the emission data. So following this result, we can see that the xylene, toluene, and the ethylbenzene, their nighttime pattern are close. But for styrene, we can see that it's overestimate at night. But for benzene, we can see that the benzene inventory data are a little underestimate, but the model species is overestimate. So let's take a look for a preliminary result summary and the future plan. The US EPA NEI data for SBTEX emission have some missing data for some SCs and county, but can be estimated by the ratio of individual HAPs and the total VOC. The MTEC data compared with the model result are not excellent, but they are close enough. And the daily average results are good for xylene, toluene, and ethylbenzene. The styrene are overestimated at low concentration, but underestimated at high concentration. And there is no perfect way to estimate the real SBTEX concentration, but this study shows a method to generate high-resolution data that can be verified by the observational data. And this can help the public health exposure study. And in the future, we will apply the data fusion method to correct the error and develop the high-resolution ambient concentration map for SBTEX over the modeling domain. Thank you.